I sometimes find myself haunted by the thought of a world consumed by fire. Imagine a time, 252 million years ago, when volcanoes relentlessly spewed lava, smoke, and ash, turning the very seas acidic. It's known as the Permian period, a time of the greatest extinction our planet has ever witnessed. But it wasn't just fire. The very shape of the world was changing, and that transformation played a deadly role. During this period, known as the Lopingian, the continents were slowly merging, forming the supercontinent Pangaea. This massive landmass became a key turning point in our planet's history. Most of the continents were connected due to the collision of ancient tectonic plates, effectively closing off two major oceans, Politz and Reiko. Politz, or ancient Tethys, was a vast ocean that once separated several continental blocks. As it slowly closed due to tectonic movements, much like the Reiko Ocean between Laurentia, Baltica, and Gondwana, immense changes rippled across the planet. These oceans' gradual disappearance altered sea currents, reshaped coastlines, and influenced the migration of countless aquatic species. Of course, these shifts unfolded over millions of years. Pangaea itself took on the shape of a giant sea surrounding a large central basin. Within this basin, vast intracratonic presbasins formed, far removed from the coast. Sediments, eroded from nearby mountains, accumulated in these areas, eventually creating vast floodplains. Over time, these basins evolved into terrestrial ecosystems, boasting fertile soils, waterways, and abundant vegetation. The Hertzian ranges, also known as Boriskos, were remnants of older mountain ranges formed during the Carboniferous period's continental collisions. By the Lopingian, these ranges had begun to erode. Despite the generally dry climate, winds and rains gradually wore down the peaks, depositing sediments into the surrounding basins. These mountains slowly diminished in height. With Pangaea's near-complete formation, the circulation of seawater, both deep and superficial, what we call thermohaline circulation, became significantly more difficult. The immense land masses blocked ocean currents, drastically reducing heat exchange and the flow of vital nutrients. Consequently, the oxygenation of deep waters decreased, and some coastal inland sea areas began to stagnate. This lack of renewal contributed to extreme conditions in many ecosystems. When continental shapes obstruct the free circulation of polar or equatorial currents, entire basins can become practically isolated. In such environments, water salinity and temperature fluctuate wildly depending on the season. Surface temperatures could soar to 30 degrees Celsius under intense sunlight, while poorly mixed depths suffered from oxygen deprivation. Without constant replenishment, marine life became increasingly fragile, leaving ecosystems exceptionally vulnerable. On Pangaea's vast lands, a dry climate prevailed, with arid and semi-arid conditions dominating. The sheer size of the supercontinent isolated many regions from external influences. Far from the oceans and deprived of rain, these lands received little precipitation. Intense evaporation and periodic drying of basins left behind expansive deserts and dusty plains. Erosion from ancient mountains further shaped this landscape, scattering fine sediments that accumulated along coasts or inland. Pangaea's massive form significantly impacted life on Earth. Drought-resistant plants thrived in poor soils, while valleys formed by ancient mountain ranges sometimes provided more fertile grounds. Hardy reptiles and other animals adapted to these contrasting conditions, often congregating in areas with more readily available water. The formation of Pangaea marked a pivotal stage in Earth's history. The Lupingian period represented a chapter on the cusp of great change, signaling the end of a geological era. Around 260 million years ago, as the Permian period drew to a close, Earth bore a completely different appearance. Nearly all continents were united in a single block, surrounded by a single ocean. This vast continent endured a dry, often arid climate, with minimal rainfall and sharp seasonal contrasts. Summers were scorching, with inland temperatures exceeding 40 degrees Celsius, while winter nights sometimes plummeted to near Arctic frosts. The sheer scale of the continent amplified these extremes. During summer, it rapidly heated under the sun's rays, while in winter, it quickly shed its heat. Imagine these immense lands, largely untouched by oceanic influences. Without the thermal regulation provided by the seas, extreme temperatures became particularly pronounced. The landscape stretched across vast expanses of desert, sparse steppes, and a scattering of isolated oases. Only plants capable of withstanding prolonged droughts could endure such conditions. Animals migrated vast distances, fleeing the heat and searching for more habitable areas with water and vegetation. Yet even in these harsh conditions, life persisted. While Earth has experienced more extensive glaciations in the past, southern Pangaea, known as Gondwana, still harbored significant ice caps. However, their sizes were... I often think about the end of the Permian period, the time just before the greatest extinction event in Earth's history. It's easy to imagine a sudden cataclysm, but the truth is far more unsettling. The seas, once teeming with life, began to falter, struggling to create new forms, and this subtle signal foreshadowed the deep environmental disruptions to come. These changes were connected to the ice caps, which, while not as vast as during true ice ages, still influence sea levels. As the ice advanced, the sea retreated, sometimes by hundreds of kilometers, disrupting coastal ecosystems and forcing primitive mollusks and corals to constantly adapt. The dry climate increased the salinity of inland seas, leaving behind deposits of gypsum and salt. Many marine creatures sought refuge in warmer waters or developed strategies to survive in these harsh conditions. The atmosphere, too, was crucial. CO2 levels were relatively low, between 350 and 450 ppm, but the oxygen content reached nearly 30%, significantly higher than today. This abundance of oxygen fueled the metabolism of many species, but also increased the risk of wildfires, turning dry landscapes into giant infernos. Despite the growing crisis, biodiversity remained surprisingly dynamic. In the shallow seas, brachiopods attached to the seabed filtered nutrients. Bryozoans formed calcareous colonies, resembling small reefs that sheltered other invertebrates. Fusulinids, single-celled protozoans with spiral shells, grew to impressive sizes, their abundance making them useful for dating sedimentary rock layers. Gondwana, the supercontinent encompassing Africa, Australia, South America, Antarctica, and India, was covered in vast forests of Glossopteris, seed-bearing deciduous plants that thrived in moist soils with distinct seasons. Alongside them grew chordates with long ribbon-like leaves, ancestors of modern conifers. These forests provided shelter for insects and animals, enriching the soil and regulating water levels. In the semi-arid plains, synapsid therapsids, ancestors of mammals, and pariasaurs, heavily armored reptiles, roamed. Among the therapsids, the dicynodonts stood out as herbivorous giants with massive bodies, tusks, and horny beaks adapted for grinding tough plants. The pariasaurs, with their bony plates and powerful jaws, inspired respect and intimidated predators. In this landscape, marine and terrestrial life harmoniously complemented each other. Brachiopods, bryozoans, and fusilids thrived in oxygenated, nutrient-rich oceans. Dense forests of Glossopteris and chordates provided shelter and enriched the soil. Synapsid therapsids and pariasaurs grazed on the plains. This living mosaic was the result of slow evolution and precise environmental adjustments. The brachiopods survived by filter feeding. The bryozoans formed colonies housing other species, and the microscopic fusilids left behind remarkable fossil layers. In Gondwana, lush vegetation supported a balanced food cycle of insects and vertebrates, with synapsid therapsids and reptiles demonstrating diverse adaptations. Large herbivores and predators sought prey, maintaining the ecosystem balance under a relatively stable climate. I find myself haunted by the image of red tides. Imagine coastal waters, once vibrant with life, now stained a disturbing crimson. Sediments whisper tales of massive mortality, entire ecosystems collapsing under the weight of oxygen deprivation. These aren't isolated incidents, but rather a symptom of a global degradation, a growing vulnerability in our marine environments. The intense color comes from bacteria thriving in these oxygen-starved conditions. As they flourish, they release compounds that oxidize dissolved iron, leaving reddish deposits on the seabed. The continents, too, play a role, with nutrients flowing into the oceans, fueling microorganism blooms that greedily consume what little oxygen remains. In stagnant, overheated waters, oxygen levels can plummet, leading to mass extinctions. Another sign is the increasing ratio of strontium isotopes in the oceans, specifically the isotope 87. This indicates accelerated erosion of the continental crust, releasing more of this element into the marine environment. It's like the rocks themselves are sending a warning signal. Tectonic activity exposes vast areas to weathering, while erratic rainfall patterns cause flash floods, carrying sediment into the seas. This disrupts the delicate chemical balance, fostering anoxic conditions. Geochemical samples reveal an accumulation of terrigenous particles and a decline in local biodiversity. Marine communities weaken, food chains break down, and geochemical disturbances amplify. These are all alarm bells, signaling that the ocean's resilience is failing. These changes are recorded in sedimentary archives, in fossil layers, and the convergence of these indicators marks a turning point. Even now, life is trying to adapt, but the environmental tension is building. These are the first signs, foreshadowing global changes. It reminds me of the events that unfolded roughly 253 million years ago, with the formation of the Siberian Traps, one of the largest volcanic formations we know of. To understand it, we must delve into the composition of magmas rising from the Earth's mantle. These basaltic magmas, rich in iron and magnesium, have a distinct chemical signature. As they ascend, they interact with upper geological layers, especially carbonate and evaporate rocks formed from the evaporation of ancient shallow seas. This interaction created a network of underground structures, dikes, sills, and diatremes. Imagine a vast network where molten rock once circulated in immense quantities. Imagine an underground construction site, vast and unseen, deepening the Earth's lithosphere by hundreds, even thousands of meters. It was here, long before the lava reached the surface, that the end of the Permian period began to take shape. Gas emissions were already occurring at considerable depth. The heat from the magma, you see, destroyed rocks rich in organic matter and carbonates, causing them to burst. Lava reached the surface through faults and volcanic channels, releasing biogenic methane, a product of the decomposition of ancient organisms trapped in sediments. This methane, under the influence of magma, was released, entering the atmosphere or groundwater. Carbonate rocks released carbon dioxide and organic layers, methane. Over a short geological period, these greenhouse gases were released into the environment, profoundly changing the chemical balances of that time. Think of an active magmatic zone developing in successive waves. First, primary igneous veins formed, reaching the lower crust. Then, under press, new corridors appeared, breaking apart the upper layers and allowing ever larger volumes of molten rock to pass through. At each stage, the heat changed the chemical composition of the surrounding sediments, leading to the early release of gas. This initial phase, though invisible on the surface, had a significant impact on the atmosphere and oceans. The large quantities of carbon dioxide and methane retained heat, changing the climate and disrupting the chemical composition of sea waters when dissolved. Scientists believe that this gas release contributed to environmental instability even before the first lava eruptions began. The Siberian traps that we see today are merely the impressive remains of a colossal magmatic activity. The huge basalt plateaus are only a small part of the initial underground invasions. No one at the time could have imagined that lava flows would reach heights of several thousand meters and cover such a vast area. It all started with magma seeping through the evaporate and carbonate crust, forming dikes, sills, and diatremes. This marked the beginning of one of the largest chains of geological and climatic events in Earth's history. About 252 million years ago, our planet experienced unprecedented volcanic activity. For 60,000 years, huge lava flows with a volume of more than 10 cubic kilometers per year were ejected into the atmosphere. This invasion began in modern-day Siberia, destabilizing already fragile ecosystems. The eruption rate surpassed anything the planet had ever seen, becoming a turning point in the history of life. The force of the eruptions emitted gases and particles into the stratosphere, significantly changing the climate and atmosphere. Sulfur dioxide was particularly important. Rising with the magma, this gas reacted with water vapor to form sulfate aerosols, tiny particles capable of reflecting sunlight. For several years, this led to a temporary cooling of the climate by several degrees, weakening organisms already under press. When the temperature dropped sharply and light levels decreased, ecosystems struggled to adapt. Sulfate aerosols don't stay in the atmosphere for long, returning as rain after a few years. But volcanic activity, unceasing for tens of thousands of years, constantly brought new flows. This led to a cycle of recurring cold spells, lasting for tens of thousands of years, causing climatic upheavals and replacing species. Many declined or disappeared altogether. In addition to sulfur dioxide, substances like chlorine and mercury were released into the atmosphere. Chlorine can deplete the stratospheric ozone layer, increasing the effects of ultraviolet radiation. Mercury pollutes soils and oceans for a long time, threatening animal and plant life. All these gases and particles caused complex reactions in the atmosphere, creating an unstable, dangerous, and unpredictable environment. On land and at sea, living things faced a complex and interconnected set of threats. The scale of this volcanic activity is measured not only by the volume of lava, but also by the amount of gas emitted. Every year we observe the emission of more than 10 cubic kilometers of magma, which is one of the largest recorded episodes. Imagine a flow capable of covering a large city in just a few years. According to the most accurate data, this peak intensity lasted only a few tens of thousands of years. In geological terms, this is a short period, but it was enough to significantly affect the climate. These huge emissions caused rapid and repeated changes in atmospheric chemistry, accelerating global imbalance. Successive lava flows and released gases caused a wave effect. Each eruption released new aerosols into the atmosphere, dispersing them and blocking sunlight, which again caused a temporary cooling of the planet. Then began a cycle of oscillatory climate changes directly related to the intensity and frequency of eruptions. Ash particles that entered the stratosphere remained there for several years before falling and forming new layers. The lands, often covered with ash, changed the soil, disrupting the local flora and the entire food chain. I've spent countless hours analyzing the rock layers from that unique volcanic period. By studying the chemistry of the sediments and the nature of the minerals using precise dating methods, I've been able to track the duration and intensity of each phase of the eruption. This data helps us understand the Earth's capacity to emit huge amounts of gases and particles, gases that can affect our climate for the long term. The cooling caused by sulfate aerosols was only temporary, but it left such a deep mark on the history of our planet. These repeated eruptions were evidence of the incredible power that lurks deep within the Earth. For living beings, such rapid changes became a true challenge. It's a stark reminder that the Earth remains a living, unstable world, driven by deep, sometimes uncontrollable mechanisms. I consider this period to be a crucial turning point in the history of life. At that time, the temperature on the Earth's surface dropped sharply by about 5 degrees. To me, this change, I use oxygen isotope analysis of microfossils known as canodonts. These small, now extinct marine organisms possessed unique structures that reminded some early researchers of small teeth. The composition of their fossils allows us to track temperature fluctuations and reconstruct the climate of the past. This material, consisting of calcium phosphate, has an amazing ability to persist in sediments, making it an invaluable source for researchers like me. It stores information about changes in the chemical composition of seawater at that time. As the ocean temperature changed, so did the ratio of oxygen isotopes in these microscopic structures. By comparing samples taken from different periods, I can assess past thermal fluctuations. That sharp, cold snap had a serious impact on fauna and flora, causing physiological stress in many plants. Glossopterium was particularly affected, a group of seed ferns that dominated the Gondwanan landscape at the time. A sudden cold snap disrupted their growth cycle, leading to a rapid decline in their population. The sudden disappearance of Glossopteris demonstrates how a sharp drop in temperature can trigger a chain reaction. Less vegetation, less soil, unstable, degraded ecosystems, and weakened food chains are all a result of the destruction of vegetation cover. These plants played a vital role in nature, absorbing carbon dioxide, producing organic matter, and maintaining soil moisture. Their disappearance seriously disrupted the balance of ecosystems. The cold snap also had a significant impact on soil erosion. Without plant cover and already weakened by the climate, the soils became more vulnerable. Wind and rain accelerated their erosion, carrying large quantities of sediments and nutrients into nearby seas. The connection between cooling and enrichment of the seas may seem paradoxical. However, when soil erosion accelerates, it releases more phosphorus, potassium, and other nutrients into rivers. These elements then end up in the oceans, promoting the growth of algae and microorganisms. Although at first glance this increase in productivity may seem beneficial, sometimes it leads to imbalance. The water column becomes more stratified, mixing occurs less efficiently, and the oxygen level in the water decreases. Cooling of the atmosphere and surface waters of the ocean leads to disruption of its circulation. If the water layers become too stable, they stop mixing, which hinders the access of oxygen to the depths. At the same time, nutrients coming from the continents stimulate the formation of organic matter on the surface. As this substance decomposes, oxygen present at depth is consumed. As a result, some areas find themselves in a state of anoxia or even euxenia, an oxygen-free environment saturated with hydrogen sulfide, which is toxic to marine life. Although this period is characterized by significant cooling, its impact on the climate is much more multifaceted. In addition to a simple decrease in temperature, seasonal fluctuations, disruption of the vital activity of living organisms, and imbalances in ocean circulation are closely interconnected. These factors cause chain reactions in which each element affects the rest. This chaotic climate no longer follows a linear rhythm, but rather represents a dynamic system, complex, unstable, and difficult to reverse once it has begun. As volcanic aerosols gradually dispersed into the upper atmosphere, new changes occurred. These small particles acted as a sunscreen, temporarily cooling the planet. However, beyond this protective curtain, the Earth abruptly entered a phase of global warming caused by greenhouse gases. Temperatures rose rapidly, marking a transition as sudden as it was formidable. Scientists have calculated that, as a result of the earthquakes, more than 30,000 gigatons of carbon dioxide were released into the atmosphere. Volcanic eruptions also contributed to an increase in the concentration of this gas. Carbon dioxide retains heat, redirecting part of the radiation back to Earth. This mechanism usually makes Earth habitable, but at such high levels the effect gets out of control and temperatures rise rapidly, pushing the planet into uncontrollable warming. As aerosols disappeared, another gas, methane, formed during the decomposition of organic substances began to increase warming. This gas usually remains locked in ice structures that trap it under oceans or in frozen soil. However, with a sharp increase in temperature, these ice cells began to melt, releasing huge volumes of methane. At the end of the Permian period, this massive degassing could have played a key role in accelerating global warming. The massive release of methane makes global warming worse because it is a more potent gas than carbon dioxide, at least in the short term. Once it enters the atmosphere, it forms a new layer which retains heat incredibly effectively, combined with the already large amount of carbon dioxide that was released. The Earth's temperature jumped dramatically, some estimate by as much as 8 to 10 degrees Celsius. It happened in what, geologically speaking, was the blink of an eye, less than 100,000 years. It's hard to truly grasp the speed of that change. For marine ecosystems, this rapid warming was a profound shock. The oceans, which typically act as thermal buffers, simply couldn't absorb the excess heat fast enough. Aquatic life was thrown into disarray. Corals, mollusks, and fish found themselves facing unprecedented dangers, struggling to survive, reproduce, or even breathe in these unstable temperatures. But it wasn't just the oceans. Rising temperatures significantly impacted terrestrial flora and fauna as well. Plants, so sensitive to climate, faced extreme heat and increasingly unpredictable precipitation. I think of forests in the southern hemisphere, forests accustomed to a semi-arid climate, now struggling to survive more intense droughts or sudden periods of high humidity. Animals on land fared no better. Those that could tolerate the heat or migrate to cooler regions had a better chance, but those dependent on stable habitats were the first to suffer. From a geological perspective, this global warming accelerated the erosion of continental surfaces. In some regions, the climate grew drier, while others experienced sudden, heavy rains. The slopes were destroyed, and huge volumes of sediment were carried to coastal seas. This runoff altered the chemical composition of shallow seas, weakening their ability to sustain marine life. This warming triggered a chain reaction. Every change on land eventually affected the aquatic environment. Volcanism, it turns out, played a central role in this global process. Enormous gas emissions, what some call neovolcanism, released a huge amount of gas that could change the climate. For a time, aerosols in the stratosphere caused a slight cooling, but as soon as they dissipated, the heat was trapped by the carbon dioxide and methane that remained. With an atmosphere saturated with greenhouse gases, the Earth began to descend into one of the warmest eras in its history. It's important to remember that this climate change didn't affect all regions equally. Coastal areas, better ventilated, may have weathered the initial extreme heat better than interior areas, far from the moderating influence of the oceans. But despite these local differences, the global trend remains clear. Temperatures were rising rapidly. Precipitation layers and fossil analyses confirm this, directly reflecting the enormous accumulation of volcanic gases in the atmosphere. We're entering a critical phase of geological history, a time when the ocean is undergoing a profound transformation. Acidity is increasing so rapidly that the skeletons of many species, built of limestone, are beginning to dissolve. This phenomenon is known as ocean acidification, and it corresponds to a decrease in the pH level, which measures the acidity of the water. Typically, seawater has a pH around 8.1, but at this time it could drop below 7.4. The ocean is becoming much more acidic than it has been for most of Earth's history. This sudden upheaval is mainly caused by the vast amounts of carbon dioxide being released into the atmosphere. When this gas dissolves in the ocean, it turns into carbonic acid, releasing hydrogen ions that increase the water's acidity. These excess ions reduce the amount of carbonate ions needed to form shells and skeletons. Typically, carbonate ions bind with calcium to form calcium carbonate, the main component of corals, mollusks, and other marine organisms. But as acidity increases, this reaction becomes more complex, weakening all the marine life that depends on it. Calcium carbonate, this crucial component of shells, exists in several forms. The most common and fragile of these is aragonite. To determine whether organisms can continue to produce it, scientists use an indicator known as the aragonite saturation degree, or aragonite omega. When this factor falls below 1, calcareous structures become unstable. At this moment, it falls below 0.5. Not only does it become virtually impossible to build new skeletons, but those already formed begin to dissolve. The sea gradually destroys what nature has created. This rapid acidification disrupts the entire ecosystem that depends on the strength of the reefs for survival, nutrition, and protection. Coral reefs are true oases, created by underwater inhabitants known as mitozoans. These creatures have the unique ability to produce calcium carbonate. However, with the fall of pH and a reduction in the saturation factor, almost 80% of reef production is being destroyed. Most corals and reef builders can no longer strengthen their structures, and many die before they can reproduce. The cornerstone of marine biodiversity is being destroyed before our eyes, and the disappearance of reefs threatens the entire food chain, which relies on the smallest planktonic organisms. Among these are radiolarians, tiny unicellular organisms with siliceous skeletons, and calcospheres, small calcareous vesicles. Radiolarians don't directly depend on calcium carbonate, but they are very sensitive to chemical influences. A sharp drop in pH can disrupt their metabolism, diet, and even their ability to reproduce. Calcospheres, on the other hand, are much more vulnerable. When acidity increases, their thin walls dissolve, often leading to their death. I find myself thinking about the fragility of ocean ecosystems. It's easy to imagine their collapse, a domino effect triggered by something as seemingly small as dissolving plankton shells. This isn't a temporary crisis. It's a threat to the entire marine food supply. Ocean processes, these vast and ancient systems, are on the verge of complete collapse. Even a minor imbalance in the chemical balance leads to disruptions in oxygen production and the processing of vital nutrients. Corals, the very foundation of complex ecosystems, are destroyed or cease to develop. Young fish deprived of their usual shelters become easy prey. These chemical disturbances affect not only marine fauna but also the flora, especially calcareous algae that live in reefs. These algae, which require calcium carbonate for growth and survival, encounter increasing difficulties. Their reduction accelerates reef degradation and disrupts important gas exchange processes like photosynthesis. After a sharp increase in acidity, opportunistic species often take over. Some unknown algae, taking advantage of the decline in calcareous organisms, form dense mats that deprive corals of light, leading to their death. Under extreme conditions, the ocean's biological pump, the mechanism by which plankton absorb carbon dioxide for transfer into sediment, undergoes significant changes. As the population of calcareous seafloor algae declines, less organic carbon is buried. Moreover, dissolved shells release calcium into the water, further altering the marine environment's chemical composition. This vicious cycle can lead to long-term acidification or fluctuations that prevent the ecosystem from returning to a stable equilibrium. Rapid acidification and the dissolution of carbonates cause large-scale destruction of reef life, with a loss of about 80% of metazoan production. At the same time, radiolarians, plankton, and calcospheres are in decline, threatening the very foundation of the food chain. Without these vital organisms, the upper levels, starting with zooplankton, would be under serious threat. Even the largest predators would struggle to survive in the long term. I've been reading about the Permian period, a time when the oceans experienced a dramatic upheaval. Vast areas devoid of oxygen, known as anoxic environments, emerged. The concentration of carbon dioxide in these areas was so low that most marine organisms couldn't survive. Moreover, in some of these pools, hydrogen sulfide, a highly toxic gas, accumulated, turning the ocean depths into death traps. This gas could even escape into the atmosphere. To understand the seriousness of our current situation, it's crucial to study the mechanisms that gradually rendered those ancient ecosystems uninhabitable. The main trigger for that anoxic crisis was the increase in thermal stratification of the oceans. Normally, ocean currents and temperature differences provide vertical mixing, promoting the deep penetration of oxygen and the simultaneous return of nutrients to the surface. However, when a noticeable gap arises between surface and deep waters, due to the overheating of the upper layers and the cooling of the lower ones, this mixing is interrupted. A thermal barrier forms, preventing oxygen from reaching the deeper layers. In tropical regions, the surface temperature sometimes reaches more than 30 degrees Celsius, which only worsens this separation. Deep waters become isolated from any sources of fresh oxygen, turning into traps where the small amount of remaining oxygen is quickly consumed by organisms and decomposition. Suffocation occurs rapidly. As oxygen disappears from the depths, other forms of life take its place. Microorganisms that can survive without oxygen begin to actively multiply, including certain bacteria that use sulfur as an energy source. In these oxygen-deprived conditions, sulfur dissolved in water gradually converts into hydrogen sulfide, a toxic gas with a characteristic rotten egg smell. In such extreme environments, rare bacteria like chlorobi thrive, finding a favorable environment. They carry out a special form of photosynthesis that doesn't require oxygen. Instead of obtaining energy from light and oxygen, these microorganisms directly use hydrogen sulfide. Due to their unique metabolism, they're called green sulfur bacteria, owing to the characteristic green color of their light-sensitive pigments. One of the most noticeable traces left behind by chlorobacteria in sediments are specific pigments called porphyrins. These molecules, originating from complex organic structures, are often found in large quantities in ancient rocks, such as black shales, which are rich in organic matter. In conditions where natural degradation is slowed due to a lack of oxygen, bodies of water accumulate remains that haven't fully decomposed. During this incomplete decomposition, several compounds are released, including the characteristic green sulfur pigments. When geologists discover these porphyrins in sedimentary layers, they can conclude that in ancient times there was an oxygen-free environment, often saturated with gray. In other cases, they speak of euxinic conditions, the gradual onset of complete anoxia, followed by confirmed anoxia, has serious consequences for marine life. Seabed animals such as mollusks, brachiopods, and crustaceans can no longer survive in such conditions due to a lack of oxygen. Sensitive species gradually disappear, leading to the collapse of the food chain and food shortages. Even surface organisms, which are still partially saturated. I sometimes imagine the end of the Permian period as a slow-motion nightmare. Not a sudden bang, but a creeping suffocation. The oceans, once vibrant, faced a growing crisis, a deficiency of oxygen, a reduction in vital nutrients from the deep. Fish, I read, began avoiding areas saturated with hydrogen sulfide, that insidious gas that attacks their ability to breathe. And at depths dominated by green and sulfur bacteria, this gas could accumulate in truly terrifying quantities. This threat wasn't just local. The hydrogen sulfide could rise into the atmosphere, especially if the climate shifted, or if geological upheavals caused deep waters to surge upwards. We've seen echoes of this in modern seas, but nothing on the scale that likely unfolded at the close of the Permian. The massive eruptions and global warming probably amplified thermal stratification, essentially trapping sulfur-saturated waters below. A sudden release of this would have been catastrophic. Hydrogen sulfide is lethal to most organisms that rely on dioxygen, our familiar oxygen. The consequences for life, both in the seas and on land, would have been staggering. On the continents, winds could have carried sulfur gases from the coasts, poisoning ecosystems. Air pollution would have reached levels we can barely imagine. Even the hardiest plants couldn't withstand such high concentrations of harmful substances, especially hydrogen sulfide. The combination of toxic air and soil contaminated with sulfur deposits would have accelerated the extinction process. It wasn't instantaneous, this die-off. It was uneven. Some areas, better ventilated or exposed to currents, might have temporarily resisted the oxygen depletion. But in many parts of the ocean, euxinic conditions prevailed, leading to the death of almost everything. The geological record is stark. Changes in sulfur isotopes reveal hydrogen sulfide's central role in the chemical transformation of sediments. These traces allow researchers to date euxinic episodes, the extent of oxygen-deprived zones, and track their evolution. This interdisciplinary approach, combining stratigraphy, sedimentology, and biogeochemistry, sheds light on these ancient mass extinctions. This vision of an ocean starved of oxygen and saturated with hydrogen sulfide is one of the darkest chapters in the history of marine life. It demonstrates how strong thermal stratification, limiting the exchange between surface and depths, can trigger a chain reaction leading to widespread death. We're looking at a crucial juncture where marine life experienced one of its most profound crises: major extinctions. Oceans once teeming with life began to decline. Almost 95% of the remaining brachiopods and trilobites vanished suddenly. These two groups, so important on the seabed, played a crucial role in water filtration and providing habitat. Their rapid disappearance demonstrates how deeply this crisis affected the entire food chain. Even sharks such as Shinocanthus and Acanthoda found themselves on the brink. Shinocanthus, easily recognizable by its prominent spine and slender silhouette, lived in both seas and fresh water. Acanthodians represented an important evolutionary step for vertebrates. As predators feeding on small crustaceans, they were crucial to the balance of the ecosystem. Their disappearance created a deep ecological vacuum, a break in the chain that could impact long-term food security. And it wasn't just isolated species. Reefs, those vibrant centers of biodiversity, were decimated. They depended heavily on sponges and bryozoans, small colonial organisms that together created strong underwater structures. The sponges actively filtered particles, creating favorable niches for other species. The bryozoans stabilized the seabed and provided habitat for many invertebrates. With their disappearance, an entire network of vital interactions disintegrated. To truly appreciate the scale of this catastrophe, we need to understand the reef builder's critical role in the marine balance. When reefs are destroyed, the habitat of thousands of species is lost. Fish, crustaceans, mollusks all lose the shelter they need for food, reproduction, and protection. Many researchers believe that the disappearance of these biological structures is a key factor behind the significant reduction in marine biodiversity. Under normal conditions, filter-feeding organisms like sponges and bryozoan colonies provide stable primary production, which forms the foundation of the food chain. Without this foundation, the entire chain begins to collapse. The mass extinction of brachiopods and trilobites weakened food chains significantly. Brachiopods, with their two shells like those of clams, filtered out small organic particles and served as food for specialized predators. Trilobites, among the oldest and most common marine arthropods, played a vital role in processing waste and also served as prey. Their simultaneous loss caused a cascading collapse of interactions in the food chain, leading to irreversible ecosystem imbalances. Paleontological studies of sediments show that the disappearance of many marine groups occurred very rapidly on a geological scale. Fossil analysis reveals how sudden the disappearance of many species of fish, as well as shells and carapaces, indicates large-scale changes in the ocean ecosystem. Scientists have discovered that several interrelated factors contributed to this. Researchers studying the chemical composition of the marine environment have been able to recreate the unstable climate of the time using stable isotopes. they discovered increased acidification. I often wonder what it must have been like to witness an ecosystem collapse, what it would have felt like to see the very foundations of life crumble. During the Permian extinction, the ocean ecosystem did just that. The marine organisms, already weakened by anoxia in the deep waters, simply couldn't withstand the additional stress. The large predators dwindled first, lacking prey, followed by the intermediate species. The seabed, once teeming with life, was deprived of its key inhabitants. Reefs collapsed. Fish populations were decimated. The end of the Permian wasn't just a marine tragedy. It was a time of immense change for life on land as well. The continental biosphere faced impacts that dramatically altered entire ecosystems. The oxygen-rich atmosphere, once a source of life, fueled fires on a scale never seen before. Fueled by rising temperatures and an arid climate, these fires consumed vast forests of primitive conifers and other plants. They raged across hundreds of kilometers, accelerating deforestation and releasing massive amounts of carbon dioxide, exacerbating the greenhouse effect and driving global warming even further. The wind-blown ash and rains enriched the aquatic environment, stimulating reproduction in some areas but also leading to a decrease in dissolved oxygen as organic matter rapidly decomposed. The massive deforestation also left the terrestrial ecosystem vulnerable. Without plant protection, the soil eroded faster, and sunlight, once filtered by the forest canopy, baked the earth. Animals lost their food and shelter, finding themselves in an unfamiliar and hostile environment. Large herbivores, adapted to abundant foliage, faced starvation. Once rich forests became scorched, fragmented landscapes. Only a few areas retained their former beauty, offering little refuge from the fires. The land population dwindled against this backdrop of ecological destruction and shifting weather patterns. The crisis directly impacted tetrapods, the four-legged vertebrates, including the therapsids, those often forgotten creatures that were the distant ancestors of modern mammals. Even then, therapsids were varied, thriving in semi-arid plains using scattered forests for life and reproduction. But the increase in fires and the rapid transformation of ecosystems decimated their shelters, endangering already vulnerable populations. The forces at play caused a large-scale collapse of tetrapod diversity, with about 70% of species disappearing, including many therapsids. Those that couldn't adapt suffered the most. Large herbivorous lines, dependent on abundant vegetation, almost vanished. The number of predators declined as well, lacking prey. Regions once rich in wildlife became deserted. Even resilient environments like wetlands and marshes suffered serious damage. Erosion led to the accumulation of excess ash and nutrients, disrupting the ecological balance. Migration corridors fragmented, and many species could no longer reproduce due to the lack of suitable habitat. The integrity of the food chain was shattered. Dinosaurs hadn't yet appeared, and only a few relatively robust or lucky lineages survived. They would eventually become massive, preserving their evolutionary advantage for the next era. The disappearance of the therapsids and other four-legged animals opened up ecological niches that would become favorable for the emergence of new life forms in the Triassic period. But at the moment, the situation was dire. Terrestrial fauna was endangered, Forests were being destroyed, and landscapes were rapidly degrading. During this critical period, intense volcanic activity released vast quantities of toxic gases, including halogens like chlorine, sulfonate, and bromine. These gases, reaching the stratosphere, interacted with the ozone layer, the planet's shield against harmful solar radiation. Halogen atoms triggered chain reactions that destroyed the ozone layer. A single chlorine atom, for example, could split ozone molecules into oxygen and chlorine oxide, which in turn attacked other ozone molecules, worsening the problem. The ozone layer thinned rapidly, allowing dangerous ultraviolet rays to reach the Earth's surface in unprecedented quantities. This radiation, mainly ultraviolet B, is usually filtered by the ozone layer. But at the end of the Permian, its weakening allowed these harmful rays to reach the surface, causing burns on the skin of animals, changes in plant cells, and disturbances in cell division. Plants that required photosynthesis suffered particularly. Profound mutations were even discovered in fossilized pollen grains from that era. I've spent years studying extinction events, but the Permian extinction still haunts me. Imagine a world where the very air and water turn against life, where the protective shield of the ozone layer weakens and the sun's rays become a weapon. That's what the evidence suggests happened then. The data points to ultraviolet B radiation, intensified by ozone depletion, damaging the genetic material of plants. This, in turn, weakened their ability to reproduce, leading to a decline in plant diversity. Forests, already struggling with heat and resource scarcity, experienced a significant decrease in their natural regeneration. And it wasn't just the radiation. Volcanic activity released gases like sulfur dioxide and hydrogen chloride, contributing to acid rain. These compounds dissolved in atmospheric water, forming sulfuric acid that scorched the earth. It burned leaves, weakened roots, and altered the chemical composition of the soil, making plant survival even more difficult. This disruption cascaded through the ecosystem. Herbivores already struggling found their food sources dwindling as forests and meadows could no longer provide sufficient sustenance. Forced to travel long distances in search of food, they faced unfamiliar and often hostile environments, further disrupting the food balance and increasing the overall instability of the ecosystem. The scientists I've read concluded that the combination of massive volcanic emissions and ozone layer destruction was the cause of one of the most severe extinction events in Earth's history. The consequences varied by region, but the core mechanism remained the same. Without the protective ozone layer, ultraviolet radiation reached levels sufficient to disrupt DNA replication. Simultaneously, acid rain caused by sulfur and other volcanic gases weakened ecosystems already on the brink of collapse. As volcanic halogens disrupted the upper atmosphere, life on Earth faced multiple threats. Plant spores and seeds of coniferous trees showed developmental defects, indicating severe environmental stress. On land, forests rapidly declined, giving way to barren landscapes prone to erosion. Soil degradation altered the way sunlight was reflected, disrupting the heat balance. The disappearance of vegetation also affected air humidity and precipitation patterns, leading to greater climatic instability. This spiral of change influenced the global evolution of the biosphere. Then there's the 10th stage, marked by a peak of sulfide anoxia and global accumulation of pyrite. During this period, the oceans were deprived of oxygen and saturated with hydrogen sulfide, a toxic gas that threatened most forms of life. This turned vast coastal areas into oxygen-deprived traps where sediments became sites of intense sulfur activity. Hydrogen sulfide in the water reacted quickly with dissolved iron, forming pyrite, iron disulfide, recognizable by its golden yellow hue. The sudden appearance of pyrite indicates anoxia caused by sulfur, sharply reducing oxygen levels in coastal areas and leading to a significant decrease in the concentration of molybdenum and uranium. These metals, usually dissolved in water, vanished in the oxygen-deprived environment. This phenomenon represents a major challenge for geologists because it indicates significant changes in the composition of the oceanic environment. Organisms that depended on oxygen-rich environments died en masse, as evidenced by fossils found in corresponding layers. Many species couldn't survive this chemical disorder. Copper sometimes accumulated in stratiform layers, indicating the precipitation of sulfides which trap metal ions. These deposits darkened, forming what we call black layers, rich in organic matter and minerals including sulfur. The presence of sulfur sometimes predicts the formation of future deposits suitable for development. Core samples demonstrate a clear transition between rich faunal deposits and these black layers where sulfides predominate. Pyrite, a witness to changes in the suffocating environment, became home to very few marine inhabitants. Its presence indicates a transition to conditions where oxygen was scarce. When deposited in rocks, these sulfur minerals changed the structure of the sediments. Copper, attracted by sulfides, could accumulate in such places in sufficient quantities to form mineral deposits later on. These layers demonstrate the scale of destruction at the end of the Permian period. The lack of oxygen was caused by intense volcanic activity and rising carbon dioxide levels, which slowed down water circulation. Deep, stagnant waters became enriched with sulfur. A detailed study of these mineralized horizons provides valuable information about the relationships between volcanism, ocean chemistry, and ecosystems. At the end of the Permian period, a huge amount of carbon dioxide accumulated in the atmosphere, contributing to a greenhouse effect. Volcanic processes significantly influenced the chemical composition of the oceans. Sediments preserved from those times show that the levels of some metals decreased, while sulfide levels increased. This indicates the extreme vulnerability of marine ecosystems. This ancient phenomenon clearly demonstrates how climate and life respond to drastic changes in the carbon cycle and ocean currents. Today, these pyritic deposits serve as a kind of mirror, helping us understand. I sometimes think about how a seemingly stable world can change in an instant, how life itself can be threatened, how the very history of our planet can be. We stand on the threshold of such a turning point, not unlike what occurred approximately 252 million years ago. The transition from the Permian to the Triassic period was marked by a mass extinction, the largest ever recorded. This cataclysm left its mark in a thin, gray geological layer, a mere 10 to 20 centimeters thick, Yet within that sliver of Earth lies a story of profound devastation. It contains fullerenes, carbon molecules shaped like hollow spheres, often formed by geological or cosmic events, and an unusual concentration of mercury, a telltale sign of intense volcanic activity or severe environmental disruption. To truly grasp the significance of this gray layer, I have to consider the concept of marine productivity. This is the ability of photosynthetic organisms, like algae and plants, to produce organic matter using sunlight and nutrients. When this process falters, the entire food chain collapses. Researchers believe that at the end of the Permian period, productivity plummeted to less than 5% of its normal levels. The ocean, once teeming with life, became a wasteland, incapable of sustaining most marine organisms. On land, the vanishing of plants further decimated resources for herbivores and omnivores, deepening the global crisis. This gray layer is often found in sedimentary deposits with abnormally high concentrations of fullerenes and mercury. Fullerenes, those carbon compounds, are typically associated with catastrophic events like asteroid impacts or massive volcanic activity. Their presence suggests widespread volcanic emissions, perhaps triggered by large-scale degassing of the Earth's crust. Mercury, released by volcanoes or the erosion of mercury-rich rocks, is another key indicator. Its high concentration in sediments points to volcanic activity powerful enough to alter the climate and ocean chemistry. Adding to this geological evidence, a sharp decline in primary productivity signals the sudden collapse of ecosystems. Fossils of plankton, corals, and reef organisms become scarce, indicating a dramatic loss of marine life. This extinction, coupled with the collapse of terrestrial ecosystems, was exceptional in its scale. As the ocean became unable to sustain life, the food chain broke down, leading to the demise of countless marine and land species. What fascinates geologists is the speed at which this extinction occurred. Estimates suggest it happened in less than 60,000 years. This dating relies on the decay of uranium into lead and zircon crystals, tiny minerals formed in magma that trap uranium within them. By measuring the uranium-to-lead ratio, we can date the formation of these crystals. Research indicates that the most critical phase of the crisis, marked by the appearance of the gray layer, occurred in a geologically short period, far less than 1,000,000 years. Why is this period so remarkable? Because in geological terms, 60,000 years is practically an instant. Such a rapid extinction suggests a sudden, powerful shock. It was likely caused by a confluence of factors: massive volcanic eruptions, ocean acidification, fluctuating sea levels, and air pollution. Together, these elements transformed ecosystems to such an extent that they led to the collapse of numerous biological communities. At that time, the Earth became depopulated, having lost a significant portion of its fauna and flora. Countless creatures perished, from the last trilobites to the large Permian reptiles. The oceans, once abundant with fish and invertebrates, became barren almost overnight. On land, most vertebrates teetered on the brink of extinction, vanishing from the face of the Earth. The survivors inherited a desolate world where a thin gray layer, devoid of fossils, bore witness to the extinction of life. With each extinction, the food chain collapsed faster. Forests receded, leaving only a few highly resilient plant species capable of survival. Returning to the gray layer, its thickness may seem insignificant compared to millions of years of geological deposits. However, it encapsulates traces of sudden changes, chemical shocks, biological disasters, and sedimentary processes. The fullerenes and mercury within it serve as indicators of this sudden degradation. Accurate dating using the zircon-uranium lead method confirms that this rupture occurred abruptly in time, marking the chaotic transition from the Permian to the Triassic and the gradual restructuring of ecosystems. This period remains one of the most significant biological catastrophes in history. This crisis was unprecedented in its severity, reminding us that the Earth, despite its apparent strength, can be surprisingly fragile. Just a few centimeters of sediment can reveal colossal disturbances imprinted in a short geological moment. As the intense volcanic activity of the Permian period subsided, ecosystems underwent profound transformations. Life in the oceans, they were becoming strange. Even species that had weathered past extinction events were vanishing, or their populations dwindled to almost nothing. Scientists began to speak of a sterile sea. The seabed, once teeming with life, showed no signs of it. I remember reading about how corals, large mollusks, and other organisms dependent on oxygen were disappearing almost entirely from the sediments. The fossil record itself was fading. Even the wind-blown tracks, the marks left by burrowing creatures, spoke volumes about the dire situation. Analyzing the bottom sediments, we can see just how much marine biodiversity collapsed. These sediments, once a network of tunnels dug by worms, crustaceans, and small fish, were now almost barren. The mobile organisms that once stirred the seabed were gone. A lack of oxygen and food, coupled with chemical changes, had transformed the seabed into a silent, deserted landscape. And the continents? They weren't faring much better. Barren soils were intensely eroded. Impressive formations known as lavas appeared, deep gullies carved into the slopes, carrying away vast amounts of soil with each rainfall. Without roots to hold the earth, even a light drizzle could form these gullies. Surfaces exposed like this were sometimes colonized by thin microbial layers formed by cyanobacteria. Microorganisms and other microscopic creatures were almost the only ones able to survive in these harsh conditions, where plants struggled to grow. These microbial layers, simple communities, supported the most primitive forms of life. During photosynthesis, they absorbed sunlight and released tiny bubbles of oxygen, but they also produced chemicals that could be toxic to more complex organisms. Their dominance signaled the extreme impoverishment of the terrestrial environment. In this devastated world, the food chain was reduced to microorganisms and a few hardy invertebrates. Animals needing a lot of oxygen almost completely disappeared, leaving behind a nearly lifeless landscape. Globally, the carbon cycle was undergoing profound changes. Large forests and marine calcifying organisms, which once absorbed vast amounts of carbon dioxide and helped regulate the climate, were practically gone. Microbial respiration, the decomposition of organic matter by bacteria, dominated the carbon cycle, releasing carbon dioxide. Fermentation also occurred as microorganisms converted sugars into acids or alcohols, sometimes releasing other gases. This new dynamic only worsened climate instability. In this desert world, with its vanished vegetation, microbial colonies covered much of the surface. Along shallow rivers and former floodplains, large green-brown gelatinous spots appeared, inhabited by single-celled algae and specialized bacteria. These spots dried out in the sun and then were saturated again by rare rains, creating alternating dry and wet phases that made it even harder for higher plants to return. Winds carried dust and abrasive particles. In some places, trees stood, but without foliage. In the oceans, despite the biological desert, some species persisted. Chemosynthetic bacteria remained viable, drawing energy from dissolved minerals, mainly around hydrothermal vents, where geothermal heat created rare refuges. But these areas were too small to support biodiversity comparable to what came before. The near absence of predators made food hunting much easier down the food chains. Studies of bottom sediments revealed a large-scale collapse of ecological interactions. There were simply too few survivors to stop the process. The Earth, having survived this collapse, appeared in a new, almost unrecognizable form. The continents were nearly empty, covered with layers of bacteria, and the oceans were struggling to regain their viability. For geologists, this period represents one of the lowest points for life on our planet, a kind of ecological reboot. The few fossils discovered indicate that simplified communities dominated at that time. In this harsh landscape, microbial respiration and fermentation became the main processes, leaving their mark in the form of an even distribution of carbon across the planet. It would take millions of years to regain true biological complexity. Between 251.8 million and 251.5 million years ago, new cracks appeared on the supercontinent, opening the way for colossal amounts of basaltic lava and gases, including carbon dioxide and helium-3. The carbon dioxide significantly increased the greenhouse effect, causing rapid warming. As for helium-3, much less common, it reveals the origins of magma deep in the Earth's mantle. These eruptions, following long periods of calm, covered hundreds of kilometers and accumulated lava flows, changing the landscape. Meanwhile, the continued accumulation of greenhouse gases led to a sharp increase in global temperatures, especially in tropical regions. Surface water temperatures rose above 40 degrees Celsius, a threshold rarely reached in the history of the planet. In these superheated seas with low oxygen levels, marine organisms, from small invertebrates to large fish, fought for survival. Reefs, already weakened by previous crises, faced unbearable thermal loads, hindering their recovery and even leading to their complete extinction in some coastal areas. On the continents, severe droughts took hold. I've often wondered how life claws its way back from the brink. Consider a world ravaged by extreme drought, plains that were once fertile, transformed into deserts. It's hard to imagine the resilience it takes to survive in such desolation, to be one of the few plants, like certain species of elk or those with larger seeds, that can endure where aquifers still offer a bit of moisture. When we speak of extreme drought, we're talking about prolonged periods without rain, coupled with intense heat and relentless sunlight. This, as you might expect, accelerates the evaporation of what little water remains, placing immense stress on land animals. It was especially brutal for the large primitive reptiles and the last of the synapsids, creatures so dependent on water for cooling and hydration. As the drought persisted, vegetation vanished, diminishing both shelter and food. The relentless cycle of dry weather left soils incredibly vulnerable to erosion. Stripped bare, they were at the mercy of fierce winds and rains which swept massive amounts of sediment into the sea. Then the coastal waters became cloudy, a phenomenon known as turbidity. This opacity blocked the sunlight essential for algae and other photosynthetic organisms. Primary production plummeted once more, further weakening the marine food chain. Geologically, this period was marked by powerful magma migrations, the result of deep faults forming in the Earth's crust. Under immense press, magmatic fluid surged towards the surface through a network of dikes and veins, penetrating deep into the rocks. This ascent was accompanied by a sudden release of gases from the mantle, notably carbon dioxide, a potent greenhouse gas, and helium-3, a telltale sign of the ancient origins of these processes. After a period of intense volcanic activity in Siberia, the geological activity began to subside. Around 251 million years ago, the igneous flow responsible for the vast lava plateau started to diminish. The basalt flows and underground fury, once so frequent, became less pronounced. This pause occurred at a time when the Earth's crust had already undergone profound changes, directly impacting ecosystems and major geochemical cycles. During this time, tectonic activity in Siberia began to weaken. The forces that had previously driven magma to the surface lessened, and the faults that had opened earlier started to close. The rise of magma gradually slowed, leading to a period of relative stability. Seismic tremors became less frequent, and landscapes once inundated with lava began a long transformation. The decline in magmatic activity also had a significant impact on the climate and atmosphere. During the eruptions, enormous quantities of volcanic gases, including carbon dioxide, were released into the atmosphere. As this flow diminished, greenhouse gas emissions slowed. Although CO2 levels remained high, there was a slight decrease in temperature. This was a gradual process, as it took time for the overall chemical equilibrium to be re-established. The reduction in volcanic emissions also allowed a key process to resume: continental silicate weathering. This phenomenon involves the transformation of silicate rocks under the influence of water, carbon dioxide, and certain organisms. As the Earth's surface cooled and stabilized, this weathering became effective once more. In the process of breaking down, stones release ions like calcium, which can react with carbon dioxide in the air. Over the long term, these reactions contribute to a gradual decrease in CO2 concentrations, playing a crucial role in the natural absorption of carbon dioxide. The calcium released from the weathering of silicates gradually combines with carbon dioxide, forming carbonates like calcite and dolomite. These minerals accumulate in sedimentary rocks, trapping CO2 from the atmosphere. For an extended period, the Earth's crust was in a state of collapse. During this time, there was a drop in temperature, and a significant amount of reactive minerals contributed to the formation of carbonates, which in turn limited the greenhouse effect. As volcanic activity in Siberia decreased, the biosphere slowly began to recover. Terrestrial ecosystems, long damaged by eruptions and extreme climatic conditions, started to return to their natural state, a slow transition to more stable conditions. Forests grew on the slopes and plains dominated by coniferous trees, rudimentary ferns, and other resilient plants. This vegetation promoted chemical weathering and the formation of soil, which in turn helped to capture carbon dioxide and stabilize the climate. The formation of new fertile soils occurred through the interaction of geological processes and biological activity. In some regions, precipitation became more regular, leading to the alkalization of minerals and accelerating their transformation. Microorganisms living in the surface layers of the soil decomposed organic matter and promoted the circulation of essential nutrients for plant growth. This process, although not entirely reliable, helped stabilize the soil, retain water, and store more carbon dioxide in developing biomass. Meanwhile, the oceans were also experiencing the effects of declining CO2 levels and reduced magma activity in Siberia. With a decrease in the amount of gases and volcanic particles in the atmosphere, the release of pollutants into the marine environment also diminished. Land erosion continued to develop actively, constantly bringing sediment into coastal areas. However, the reduction of sulfur and metal emissions created more favorable conditions for marine fauna. This chemical pause allowed plankton to begin the process of recovery, which marked the beginning of the gradual formation of more sustainable food chains. Of course, this period was just the starting point. It's almost impossible to imagine now, but there was a time when the Earth slowly began to recover from the largest biodiversity crisis in its history. It took millions of years, of course, but the planet did begin to heal itself. I find it so compelling that even after such devastation, life found a way. The processes that had restructured the continental plates were still underway, leading to instability in some sedimentary basins where flash floods or droughts caused local problems. But on a global scale, extreme events actually tended to decrease. This suggested a gradual restoration of a more stable equilibrium. Following the massive extinction of marine life, the first signs of a return began to appear on land. Although the oceans remained unstable, new organisms began to emerge, indicating some stability in ecosystems. Among these were ammonoid ceratites, small marine mollusks with spiral-shaped shells. They developed quickly, and their sutures were simpler compared to later forms. These ceratites demonstrated an opportunistic adaptation, exploiting unstable conditions that allowed them to diversify slowly but confidently. These ammonoid ceratites occupied various levels in the water column. Some lived near the surface while others preferred the deep. Their diet consisted of small plankton, and they were able to adapt to almost any conditions, reproducing quickly. As soon as conditions allowed, they occupied empty niches that became vacant after the extinction of other species. Their presence indicated that despite all the changes, the ocean no longer seemed completely abandoned. Gradually, biological activity was restored. There was also a genus of fish that lived near the ocean floor, and bivalve mollusks, chloria, that adapted to life in coastal areas where the salinity and chemical composition of the water often changed. Like ceratites, they occupied empty ecological niches, remaining after the extinction of other species. Their numbers indicated a partial restoration of marine life. Despite the still limited biodiversity, some stable centers were able to survive even in difficult conditions, such as periods of acute oxygen shortage. Meanwhile, the devastated landscapes were gradually becoming less hostile. In these open spaces, the first vascular plants to recolonize these places were lycopods, a group that includes modern flowing spike mosses with simple stems and leaves. These plants, still requiring moisture to reproduce, thrived in the absence of dominant trees. With less competition, they had easy access to light and they developed in pure or mineral soils, slowly renewing the plant world. At the same time, another amazing plant, dicroidium, appeared on the devastated lands. This seed plant was especially widespread in the southern hemisphere during the Triassic period, even though its leaves resembled those of a typical fern. Dicroidium is distinguished by the fact that it forms seeds, a trait characteristic of conifers and angiosperms. Dicroidium easily adapted to poor soils and also benefited from low competition from other plants. Its emergence marks a turning point in the reorganization of terrestrial ecosystems after the crisis. The community of lycopods and dicroidial plants were beginning to show the first signs of vegetation revival. Bringing a bit of joy to this period, long-neglected landscapes were seeing a resurgence of greenery. This process, although not complete, was an important step. Where erosion and sterility once reigned, the first plants appeared, which began to stabilize the soil, reducing runoff and retaining precipitation. The rooting of these plants helped to create microhabitats, attracting the first land invertebrates such as insects. In some places, vegetation created shade and softened the intensity of solar radiation. At this stage, with the restructuring of biogeochemical cycles, the planet was showing the first signs of chemical balance being restored. One of the most revealing indicators is delta-13 carbon, the ratio of isotopic density associated with carbonates. After falling to about 7 per 1,000, it now stabilized at around 2 per 1,000. This change indicates a decrease in the mass influx of light carbon from organic matter or volcanic emissions. This decrease in the organic signal suggests that the ocean and the atmosphere were gradually coming to a more stable equilibrium. The carbon isotope ratio, known as delta-13 carbon, was gradually stabilizing. This delta is the ratio between two isotopes of carbon, the heavier carbon-13 and the more common carbon-12, and is expressed in thousandths relative to a standard. A very negative delta indicates an excess of light carbon, often due to ancient organic matter or volcanic eruptions. However, a return to the 2 per 1,000 level indicates a more balanced contribution of organic and mineral carbon. This change reflects that the chemistry of the ocean and atmosphere were on the way to stabilization. Another positive sign was the gradual return of some microelements to the water, such as molybdenum and zinc. The marine environment is where you can find a variety of elements that serve as important indicators of the chemical state of the oceans. Molybdenum, which is necessary for nitrogen fixation, accumulates in oxygen-rich waters. Zinc, which is involved in many biological processes, also changes depending on the oxygen level. Its reappearance in sediments indicates improved ocean circulation, resulting in a more uniform distribution of oxygen and making nutrients more available to marine life. I've been studying the oceans of the early Mesozoic era, and it's remarkable how close to the edge life existed back then. I've learned that vast oceanic spaces were often euxinic, essentially toxic. These environments favored bacteria that thrived on sulfur, leaving behind specific biomarkers. These pigments and fossil molecules are like a chemical record, telling us just how aggressive, how toxic those waters were for most other species. It's fascinating to see how even small changes can signal a shift. The reduction in precipitation, for example, indicates a gradual improvement in the breathing conditions of the ocean, which then promotes the return of fish, corals, and mollusks. Active ocean circulation gives me hope, because it seems that better mixing of water allows oxygen to reach the depths, slowly displacing that oxygen-depleted water. This slight recovery, though still far from what it once was, is evidence of positive change. Corals, for instance, need a minimum amount of oxygen and a stable pH to grow, and many invertebrate filter feeders, like some marine worms, also require good oxygenation. So, this change could mark the beginning of a gradual recovery of reefs and a revival of marine biodiversity. But this improvement isn't happening everywhere at the same rate. Some ocean basins remain partially isolated, lacking proper ventilation. The slow pace of global chemical transformations makes it incredibly difficult to return to a truly natural balance. Still, this stage of reorganization is essential. Without it, marine organisms simply wouldn't be able to recover. Creating more efficient flows, gradually diluting sulfur compounds, and managing carbon emissions more responsibly are finally creating conditions for biodiversity to make a comeback. Ocean ventilation directly impacts the reproduction and distribution of species. Many marine organisms rely on planktonic larvae that need minimal oxygen to survive in the upper or middle layers of the ocean. As the anoxic conditions recede, these larvae are slowly returning to niches they once abandoned. This encourages their return, and biodiversity gradually begins to increase. Pioneer species are colonizing new territories with higher oxygen levels. One of the first signs of this process is the reappearance of wind-sensitive foraminifera. Their presence suggests that some marine sediments are becoming habitable again, paving the way for more demanding life forms. Other links in the food chain also benefit. Predators that are particularly sensitive to low oxygen levels are finding more favorable conditions. Fish, which were previously strongly affected by the euxinic environment, are beginning to move to certain plains and less aggressive seas. Even the land benefits. Winds and rains bring enriched particles that stimulate the growth of coastal vegetation. This vegetation, in turn, provides new shelters and resources for land animals, facilitating their return and development. However, even after the major Permian extinction, life wasn't smooth sailing. At the beginning of the Mesozoic era, in the early Triassic, the biosphere was shaken by two new crises, the Griesbach and Denarian events. Some organisms began to timidly explore their new environment, but instability persisted, both on land and in the sea. Reefs and many other invertebrates struggled to recover before facing serious environmental disturbances again. The first of these crises occurred during eustatic regression, a global sea retreat caused by climate or tectonic changes. This retreat further exposed already weakened reefs, disrupting water circulation and oxygen supply. In these oxygen-poor areas, corals and other organisms unable to withstand declining oxygen levels faced high mortality rates. The outflow of water also disrupted the circulation of nutrients. Marine ecosystems depend on currents that facilitate the spread of organic matter and the saturation of water with oxygen. When the water depth decreases, stagnation occurs, creating low oxygen zones where bacteria thrive, capable of surviving in such conditions. Under extreme conditions, these microbes sometimes release toxic substances which aggravates anoxia and creates a vicious cycle. Large filter-feeding organisms, such as some mollusks, had no choice but to leave these places or die, further destabilizing the local food chain. Then came the diet, the second critical phase of the early Triassic, hyperthermic impulses associated with prolonged degassing of basalt. This was a constant emission of greenhouse gases from vast volcanic provinces. Although less intense than the initial eruption, it was enough to heat the atmosphere and acidify surface waters. The combined effects of heat and acidity caused many already weakened marine invertebrates to suffer a serious reduction in survival. Acidification occurs because carbon dioxide dissolves in water, forming carbonic acid. This phenomenon, known as ocean acidification, lowers the pH level, which in turn disrupts the formation of the calcium carbonate structures essential to many marine animals. Among the most vulnerable were ammonoids, mollusks with spiral shells, and conodonts, tiny organisms known for their fossil dental elements. With increasing acidity, calcium carbonate precipitation becomes more difficult, making these species more fragile and weakened. Ammonoids and conodontians faced selective extinction during the Grisphacian period, which was characterized by high temperatures, sometimes exceeding the tolerance limits of marine organisms. Ocean warming increases the demand for oxygen while its supplies are depleted. The Great Dying. Even the name sounds like something from a story, doesn't it? But it was real. A period of selective extinction, where some evolutionary lines managed to cling to life, even diversify, while others simply vanished. I find myself often pondering the fragility of existence when I read about events like this. The fossil record shows that even as the weakened ammonoids and conodonts dwindled, other species, like live fish with strong fins, seemed to adapt more readily. It wasn't a uniform devastation, but a reshuffling of life's deck. Reef communities, those vital protectors of marine biodiversity, struggled to regain their footing. Analyzing sediments and fossils, particularly the calcified structures of conodonts, allows us to see just how quickly these changes occurred. Temperature played a crucial role in the fate of the ammonoids. They saw periods of prosperity, followed by rapid decline, a testament to the difficulty of maintaining a stable population in a world grappling with anoxia and rising temperatures. But then, slowly, between 250 and 247 million years ago, a gradual ecological recovery began. In the shallow seas, rapid diversification bloomed among live fish and gastropods. Higher up, Oromorphic arches dominated, while coniferous trees settled in humid areas, providing a more stable landscape. Carbonate platforms, those sunlit coastal formations, fostered the growth of bivalves and gastropods. Formed in warm, shallow waters from calcium carbonate and shell fragments, they became ideal havens for life. Bivalve shellfish filtered the water, seeking food, while spiral-shelled gastropods grazed on algae or collected debris from the seabed. This expansion was driven by the empty niches left by the crisis. The warm, relatively stable climate, with water temperatures between 20 and 30 degrees Celsius, boosted the reproduction of live fish and gastropod mollusks on those coastal platforms. On land, the diversity of oromorphic arches reached new heights. These primitive reptiles, related to the great Mesozoic reptiles, including long-necked protorosaurs and armored herpetologists, already showed adaptations that would help them master terrestrial habitats. The return of coniferous forests marked a turning point. Adapting to humid areas, these trees stabilized the soil, creating favorable conditions for animals. Resistant to temperature swings and unpredictable precipitation, they played a vital role, circulating nutrients from fallen needles broken down by countless organisms. Under the canopy, a variety of animals found shelter, especially in tropical areas where temperatures often climbed above 25 degrees Celsius. The trees offered protection from predators and, by absorbing CO2, helped to regulate the still unstable climate. Of course, fire remained a threat in dry areas, but the humidity of the dense forests often limited its spread. Some shrubs even developed thick bark, aiding recovery after a fire. Young shoots emerged in clearings, attracting animals in search of new territories. Live and gastropod mollusks continued to thrive in coastal waters, while archosauromorphs strengthened their presence on land. Slowly, new interactions between species emerged. Fauna and flora began to revive, enriching biodiversity. It was a slow process, and some habitats remained vulnerable. But over time, many species developed effective adaptations. Mollusks refined their feeding and defense strategies, while oromorphs adapted to the new conditions. As forests expanded, they helped to establish a more stable ecological balance. Vivariums and gastropods thrived on carbonate platforms, a testament to the resurgence of life in the oceans. Archosauromorphs hinted at the future dominance of reptiles, and the dense coniferous trees represented the strength of vegetation capable of supporting ecosystem restoration. Gradually, the planet acquired a new dynamic, showcasing life's incredible ability to recover even after the most serious shocks. As this process developed, the interactions between mollusks, reptiles, and conifers grew more complex and interdependent. Over time, the landscape began to change, with vegetation regulating humidity and temperature and protecting terrestrial vertebrates from the heat. As vegetation decomposed, it enriched the soil. In the seas, marine organisms created calcareous structures that served as support for young generations of bivalves and gastropods. This network of species, though not always coordinated, contributed to environmental stability. Despite the lasting consequences of the extinction, the period between 250 and 247 million years ago stands as a period of renewal, driven by evolutionary changes and the emergence of new forms of cooperation. On the interior plains, heavy rainfall formed temporary swamps where the first plants appeared, enriching the soil. These wetlands provided refuge for amphibians, important elements of the food chain, their presence strengthening the base of a new, slowly rebuilding world. Imagine a vast ocean struggling to recover from a long period of imbalance. I've often pictured it. Waters once warm and oxygen poor, slowly beginning to cool and delaminate. It's a moment of profound change, a turning of the tide in the most literal sense. At this point, a key phenomenon arises: thermohaline circulation. This circulation spreads deep beneath the ocean's surface, a system of currents caused by temperature differences, promoting renewal and enriching the aquatic ecosystem. The water's temperature and salinity shift, cold water sinking into the depths, carrying warmer water along. It's a natural mixing, and it improves the distribution of oxygen even in the deepest layers. For marine organisms that need even minimal oxygen, this change is critical. It's like a switch has been flipped. Deep renewal awakens life in the benthos, that community of species living on the seabed, from the smallest invertebrates to larger organisms. Even partial restoration allows weakened colonies to thrive again. As deep water circulation becomes more regular, the habitat stabilizes, precipitation disperses better, nutrients rise more efficiently, and plankton flourishes. It's as if the ocean is gradually learning to breathe again, a benefit to all life forms dependent on it. In equatorial zones, something else is happening: a decrease in chemical stratification. This occurs when layers of water with different properties, like salinity or chemical composition, begin to mix. Previously, the dynamic surface was isolated from the depths, which were poor in oxygen and stagnant. But by restoring circulation, thermohaline exchanges are enhanced and the water layers gradually mix. Nutrients rise to the surface, oxygen sinks into the depths. This mixing significantly improves living conditions for all marine life, from the smallest algae to the largest marine predators. Marine life is experiencing a boom, especially plankton. Plankton, those tiny organisms, both plant and animal, that float freely in the currents. Phytoplankton, using photosynthesis, capture solar energy and produce organic matter, which lies at the base of the food chain. Thanks to improved water circulation, these microalgae actively reproduce, attracting first zooplankton and then predators. Equatorial zones become more productive, providing new opportunities for the development of marine fauna. One of the clear signs of this vital force is the resumption of carbonate deposits consisting of calcium carbonate. These deposits are created by marine organisms, mollusks, corals, and calcareous algae, which use them to build shells and skeletons. After their death, these structures accumulate on the seafloor. As the water becomes less acidic and richer in carbonates, the sediment becomes thicker and denser, forming limestone formations. This material promotes good petrification, leaving future paleontologists valuable evidence of this biological revival. Increased carbonate accumulation also indicates an increase in benthic biomass, organisms living near the sea floor. With the return of oxygen and nutrients, underwater flora can be revived. Sedentary animals such as sponges and primitive corals find a favorable environment for the formation of new colonies. Gradually, these structures help restore reefs in a recovering ocean. They become oases of biodiversity, teeming with life. But the changes aren't limited to calcium carbonate. Microbial activity, though seemingly insignificant, significantly accelerates the decomposition of organic matter, releasing vital nutrients. Soils are enriched, promoting the rooting of life. Yet at the same time, impurities are filtered, purifying the water. Light penetrates deeper, allowing algae to continue photosynthesis. Gradually, the ocean restores its transparency, stability, and ability to regenerate. The marine world is ready for a revival. At the end of the Permian period, the configuration of the continents changed significantly. The Earth began to rift, a process that weakens the Earth's crust and opens wide faults. These are the first signs of a new ocean, marking the birth of the Western Tethys, a developing sea basin which will play a major role in the evolution of the climate and ecosystem of the Triassic. As Pangaea reached its maximum size, its central regions became arid. The seas couldn't penetrate. But the discovery of a break in the ocean changed everything. Seawater seeped through the faults, connecting the ocean with the interior areas. The new coastline provided increased humidity, softening the desert climate and increasing precipitation. Gradually, dry plains became covered with denser vegetation, paving the way for the sustainable development of many forms of animal life. The rise of warm material in the mantle created tension, gradually leading to the destruction of the Earth's crust. Over time, these cracks widened and seawater penetrated them, forming new shallow bays. Sediments brought by the sea accumulated on their shores and rivers, leading to the formation of so-called epicontinental zones, flooded with light. In these calm waters, algae and aquatic plants thrived, supporting a rich food chain. I find myself often contemplating the delicate balance that allows life to flourish, especially when I consider the deep history etched into our planet. It's humbling to realize that even the most dramatic transformations unfold over vast stretches of time, driven by forces we're only beginning to fully understand. Consider the Triassic period. It wasn't a sudden event, but a slow, almost imperceptible shift occurring over hundreds of thousands of years, marked by the erosion of mountains and the restructuring of entire river basins. As the aridity of the landscape began to recede, I imagined the winds shifting, becoming more predictable. The dry spells grew shorter, replaced by increasingly frequent rainfall. These rains, in turn, fed a burgeoning network of permanent rivers. Along the riverbanks, ferns and seed plants took root, drawing insects, amphibians, and reptiles, all hunting and breeding in this newfound haven. Gradually, these damp corridors stitched together a greener, brighter world. It was the emergence of a stable river hydrography, where water flowed reliably year-round. These weren't the seasonal rivers of the past. They were regulated by a delicate equilibrium between rainfall and the water table. This constant flow reshaped the very nature of erosion. The rivers became conduits carrying sediment rich in organic matter, depositing it in epicontinental zones. These deposits, accumulating over time, trapped carbon that had once resided in plants and animals, effectively creating stable geological reservoirs. It's a fascinating thought. the burial of organic matter playing such a crucial role in climate regulation. Normally, decomposition releases carbon dioxide, a contributor to global warming. But in oxygen-poor environments like underwater sediments, some of that carbon was locked away as kerogen, preventing its rapid oxidation. This natural storage acted as a brake, slowing down the greenhouse effect. A well-developed river system carrying vast amounts of plant debris amplified this sequestration mechanism. Along these stabilized rivers, a mosaic of habitats began to emerge, boosting ecosystem diversity. Insects, small crustaceans, and certain fish found their niche in the swamps, adapting to the more permanent waters. On land, herbivorous reptiles ventured out of their shelters, drawn by the abundance of vegetation. Slowly, distinct forests arose, populated by plants capable of enduring a variety of conditions. This very diversity fostered the gradual restoration of the entire ecosystem. Meanwhile, to the west, the Tethys Sea began its own expansion. As it opened, an arm of the rift penetrated deep inland, creating extensive coastlines, transition zones between salt and fresh water. These coasts gave rise to lagoons and estuaries teeming with life. Primitive birds and semi-aquatic reptiles began to colonize these thriving habitats. Coastal development also favored the reproduction of amphibians, creatures so adept at navigating both land and water. The stabilization of the climate during the Triassic was a pivotal moment in Earth's history. Before, carbon dioxide levels were so elevated that they triggered a powerful greenhouse effect, destabilizing ecosystems. Concentrations eventually stabilized at 800,000 parts per million. While this remains high by today's standards, it was moderate compared to the peaks of the past. Thanks to this climate moderation and the emergence of more favorable conditions, tropical temperatures hovered between 32 and 34 degrees Celsius. It might seem high, but it was influenced by the megacontinent Pangaea. This vast landmass made the interior more susceptible to climate extremes, lacking the ocean's moderating influence. Yet, life adapted. Coniferous and elk forests spread, and in the drier regions plants better suited to drought emerged. The biosphere was gradually recalibrating, achieving a new thermal equilibrium. The megacontinental nature also spurred the formation of seasonal monsoons, wind patterns that shifted dramatically with the seasons. Summers brought heavy rains, while winters were marked by prolonged droughts. This phenomenon stemmed from the temperature differences between land and ocean. In summer, the continent heated up rapidly, creating a low-press zone that drew in moist air. In winter, dry air moved toward the ocean. With the rise of vast lands during the Triassic, these exchanges reached an impressive scale. Monsoons carried immense volumes of water and sediment, reshaping landscapes and profoundly influencing the distribution of plant and animal species. Gradually, these seasonal monsoons reduced the dominance of the old deserts. More frequent rainfall encouraged seed germination in soils that were once too arid. Developing rivers carried nutrients to the coasts where marine life flourished. On the continents, fauna also found more favorable conditions. Herbivores grazed on grassy plains, and some predators adapted to the more humid environment. Forests retained their mixed character, with coniferous trees and elk coexisting, creating a microclimate that further supported a diversity of species. These diverse climatic conditions also improved nutrient cycling. During dry periods, the soil lost productivity, slowing plant growth. But with the arrival of the rains, rocks were broken down, minerals dissolved, and nutrients redistributed across the continents. This stimulated vegetation growth and supported a more diverse fauna. At sea, these rivers enriched the marine ecosystem. The regular influx of nutrients fed plankton, the foundation of the ocean's food chain, helping to sustain stable populations of fish, mollusks, and invertebrates. And primitive corals at long last found calmer, nutrient-rich waters, creating ideal conditions for the slow recovery of the reefs. I find it remarkable how even after a great crisis, nature finds a way. Resilient species occupy the niches left behind, adapting and thriving. It's a testament to the enduring power of life itself. Even the reduction in carbon dioxide levels is enhanced by oceanic sedimentation. Algae and other organisms absorb dissolved CO2, which then settles to the bottom in mineralized form. On continents, the burial of organic matter in sediments also contributes to removing carbon from the atmosphere. These combined mechanisms gradually help stabilize carbon dioxide levels, reducing the risk of the greenhouse effect. In a more stable climate, biodiversity thrives, following the logic of survival and adaptation. Reptiles adapted to the contrasting seasons are thriving thanks to new monsoons. Hardy amphibians are colonizing permanent rivers. Vegetation, less susceptible to heat stress, forms dense forests providing shelter and food for terrestrial fauna. Among the large animals, natural selection favors those that can withstand dry winters and intense precipitation. This diversity of microclimates promotes active speciation. Despite ongoing disruptions, seasonal monsoons are gradually decreasing the influence of former deserts. Rains become more frequent, allowing seeds to grow in soils that were previously too dry. Rivers develop, transporting nutrients to the coast where marine life thrives. On the continents, fauna find ideal conditions for their existence. Herbivores inhabit grassy plains, and some predators adapt to wetter conditions. Forests remain mixed, with coniferous trees and moose coexisting thanks to warmth and moisture, creating a favorable environment for many species. The diversity of climatic conditions promotes more efficient nutrient cycling. During dry periods, the soil loses its fertility, slowing down plant growth. However, with the arrival of rain, the rocks are washed away, the minerals dissolve, and nutrients are redistributed across the continents. This stimulates vegetation growth and makes fauna more diverse. In the sea, these regular inputs support plankton, the basis of the ocean food chain, which stabilizes fish populations, mollusks, and invertebrates. Primitive corals eventually find calmer waters, richer in nutrients, ideal conditions for the slow recovery of reefs. Climate change is not a sudden event. It is part of long-term geological processes, such as mountain erosion or river restructuring, which create pools that last for hundreds of thousands of years. Similarly, the reduction of carbon dioxide gas is enhanced by ocean sediments. Algae and other organisms absorb dissolved CO2 and then settle to the bottom in mineralized form. On the continents, the burial of organic matter in sediments also helps remove carbon from the atmosphere. These combined mechanisms gradually help to stabilize the level of this greenhouse gas. At this stage of geological history, new soils begin to appear on the liberated lands. Ancient Permian soils, depleted by leaching, are being replaced by more fertile structures. The environment remains complex, but certain natural processes contribute to the emergence of new soil formation. Soil formation occurs as a result of physical and chemical changes in parent rocks under the influence of water, air, and living organisms. These rocks are fragmented, and their minerals are converted into clays, which leads to the formation of specific soils such as vertisols and ispodosols, necessary for this phase of ecological reconstruction. The salt verde contains a large amount of expansive clays, which increase in volume when wet and contract during dry periods. In the late Permian, this phenomenon is aggravated by the warm and dry climate, characterized by alternating prolonged droughts and sudden rains. These changes cause the formation of cracks in the soil, which, when closed, trap organic and mineral substances, enriching the soil with nutrients. However, this mechanism also has its limitations. The movement of the soil creates significant physical and water stress, which can hinder the development of some plants. Spodosols develop in moist, acidic environments, often under dense vegetation. Their profile is characterized by a combined upper layer where water carries away soluble elements, leaving a layer poor in minerals. At greater depths, these elements precipitate in the zone of accumulation, rich in organic matter and iron. This contrast between superficial unification and deeper enrichment is typical for spadola formation. During this period, the slow erosion of the Hertzen reliefs led to the deposition of new sediments on vast plains. Under the influence of various chemical reactions, including the hydrolysis of feldspars and micas, these sediments are transformed into new clays. At the same time, organic matter from plants, such as wood fragments, accumulates and interacts with clay, initiating the first stages of the formation of rich and complex soils. Organic carbon begins to attach to the newly formed clays. When organic matter decomposes, it releases compounds that can adhere to clay surfaces. It's remarkable how soil, at a microscopic level, can stabilize carbon and keep it from returning to the atmosphere. This physico-chemical interaction, as they call it, is absolutely crucial to the carbon cycle. What I find fascinating is how this process encourages active recolonization, which in turn boosts microbial activity. Bacteria and fungi, tiny as they are, convert organic matter into the nutrients that plants need to survive. Some plants even form symbiotic relationships with mycorrhizal fungi. They give the mushrooms sugars, and the fungi help them absorb water and minerals. This microbial recolonization is especially vital after periods of crisis. Catastrophic upheavals can disrupt the soil so profoundly that only resilient communities can restore the process of nutrient processing. Mushrooms release enzymes that decompose plant appetite, which in turn releases phosphorus, potassium, and other essential elements. Over time, all of this biological activity leads to soil structuring, the formation of aggregates, better porosity, and improved water absorption. Plant roots then use this to penetrate deeper into the soil, which stabilizes the surface. This is how soil reconstruction happens, accompanied by the slow emergence of plants adapted to the constantly changing conditions. These new soils replace the Permian paleosols, which had been depleted by leaching, and contribute to ecosystem restoration. The sustainability of soil organic carbon storage acts as a climate buffer, softening temperature fluctuations and helping to restore life to the planet. The diversity of vertisols and spatisols depends on local conditions like humidity, water chemistry, and vegetation. These create a favorable mosaic for the development of microbial and plant communities, which forms the basis for the restoration of the biosphere. As these soils take shape, they become the foundation for new ecological dynamics. Nutrients accumulate. Underground fauna flourish, and the first plants encourage the formation of more diverse vegetation. Rooting limits erosion, and landscapes gradually stabilize. At the same time, the chemical evolution of the soil leads to richer habitats. We then enter the Anisian stage, a critical period between 240 and 242 million years ago. Important processes took place during this time, processes that influenced the evolution of life on Earth. Life in the late Permian slowly begins to revive after the terrible cataclysm. Ecosystems, still unstable, begin to recover, and some previously isolated groups of animals begin to flourish. New species appear in the oceans: serratitic ammonites, ray-finned fish, and the first marine reptiles, such as ichthyosaurs and nothosaurs. On land, dicynodonts and canamyariids become the dominant species, leading to significant changes in terrestrial ecosystems. Serratitic ammonites, belonging to the family of cephalopods, differ from classic ammonites by the wavy shape of their seams, the lines connecting the spiral shells. In the Anisian time, they experience a real evolutionary surge. In warm seas covering the continental shelves, they appear in various sizes and shapes. Some species have thick shells, while others have more elongated and richly decorated structures, possibly related to exhibitions or competitions. Exploring new environmental niches, they become key participants in the emerging biosphere. From the coast to the deepest waters, life is rapidly diversifying. One of the most dynamic groups of marine life is ray-finned fish. Their distinctive feature is the thin radio-osseous fins that make them much more maneuverable than primitive fish with rigid structures. This flexibility allows ray-finned fish to swim quickly and adapt to different lifestyles. During the Anisian period, these fish quickly evolve. Some hunt other fish, others filter the water, and still others burrow into the seabed or feed on algae. Their diversity reflects the full restructuring of the marine food web. Among the stars of the Anisian Sea, the first marine reptiles occupy a special place. Ichthyosaurs, with their streamlined bodies and elongated snouts, resemble modern dolphins. Their limbs have become fins, which allows them to move quickly through the water and catch fast-moving prey. Nothosaurs, on the other hand, were semi-aquatic. They could swim in coastal waters and also crawl on land to rest or lay eggs. These animals were less specialized but more versatile, using shallow areas rich in fish and crustaceans for sunbathing in tropical regions of the time. New herbivorous dicynodonts emerged on the vast continental plains from the family Canamyariidae. Its name, meaning two dog teeth, is associated with large fangs that can sometimes be seen on its back and in the front of its jaw. This powerful beast, similar to a bull, has strong limbs and a beak with horns, which allows it to effectively eat vegetation. However, its role is not limited to feeding. By clearing vegetation, it creates conditions for other animals, spreads seeds, and forms microhabitats. The rapid development of new groups reflects the major changes that occurred after the extinction. In coastal areas that were once devastated, corals, sponges, and algae are reappearing, creating shelters for fish and invertebrates. Forests of primitive trees become an ideal storehouse for decinodonts and stimulate new ecological interactions. At an average temperature of 25 to 30 degrees Celsius and improved sediment distribution, coastal ecosystems expand, while some continental areas regain their humid environment. The world is being reborn in conditions of constant warmth, and its diversity is growing. I find it remarkable how life persists even after unimaginable devastation. The explosion of diversity in this new Triassic era is nothing short of astounding. Evolution, that relentless force, continues its work, laying the foundations for a world both complex and breathtaking. In the depths of this world, reefs are slowly, painstakingly coming back to life. Sponges and algae, like silent guardians, guide this rebirth. New marine monuments emerge, the first pillars of an ecosystem striving for balance after the cataclysm. In the retreating ocean, strange builders unite. Sphintozoan sponges, with their intricate skeletons, patiently filter the water, collecting microscopic nutrients. Their internal structure promotes circulation, promoting life itself, and alongside them, the inconspicuous algae, glodals, contribute to the formation of these ecosystems. They may be invisible to the eye, but they deposit calcium carbonate, slowly building growing structures. These two silent allies, sponges and algae, feel the foundations of a new world being laid, a world where marine life can finally begin to recover. In the clear, shallow waters, where sunlight penetrates easily, a quiet revival is taking place. The ocean's chemical composition, unstable for so long, gradually returns to equilibrium. The pH level, that notorious acidity index, exceeds 7.8, signaling a more alkaline environment, favorable for calcareous structures. And the aragonite omega, measuring the water's ability to form limestone, exceeds 1.5, meaning there's sufficient calcium and carbonate for reef construction. Thanks to this restored alchemy, mineral skeletons once again gain the ability to flourish. With the return to more stable chemistry, many marine species can grow without the threat of immediate skeletal destruction. Sphincter sponges quickly seize this opportunity, settling on stones, growing rapidly, even creating entire massifs, forming solid, spongy structures that become the foundation for all marine life. In turn, algae colonize these formations, creating a thin vegetation cover that, over time, turns into limestone sediment. This layer, composed of plant remains and minerals, becomes fertile soil, ready for settlement by other species like small clams and other reef sponges. Over thousands of years, these first settlements gradually transform the underwater landscape, creating relief and opening up new ecological niches for crustaceans and fish, which find refuge and protection in the cavities of these structures. Sponges and algae, the unsung heroes, are the first participants in the restoration of marine biodiversity. Sphinthua sponges and dacyclodian algae create the very basis for future reefs, upon which exactini corals will grow. These corals are cnidarians, animals made of polyps living in colonies. Each polyp secretes calcium carbonate, gradually forming a strong collective skeleton. In the middle of the Triassic period, during the Ladinian age, these corals replaced sponges and became the main reef builders. Their success depended on favorable chemical conditions, neutral pH, and a high content of aragonite, essential for the structure's strength. The transition from sponge and algae-dominated reefs to those formed by exocetanid corals highlights the complexity of the marine balance, where water chemistry plays such a crucial role. After the initial development of a new favorable habitat, sponges and algae from Fintuas continue their evolutionary path. Dasy's pantries gradually disappear, giving way to corals which eventually form huge barrier reefs, providing a haven for diverse marine life. This renovation is a testament to life's incredible ability to recover, even after large-scale cataclysms. We are entering a decisive stage in Earth's evolution when oxidation-reduction cycles, those chemical reactions of oxidation and recovery, gradually reach equilibrium. Around 240 million years ago, this chemical balance strengthened to such an extent that a period of relative calm ensued. Oxygen in the atmosphere, after significant fluctuations, reached a stable concentration of 16 to 18%. Although lower than today, this level was still sufficient to support a huge diversity of life, both on land and at sea. The stabilization of oxygen levels wasn't accidental, but the result of a gradual decrease in the intense volcanic activity that had previously prevailed. When magma reaches the surface, it reacts chemically with rocks, releasing oxygen. During volcanic eruptions, various gases such as sulfur dioxide and mercury are released into the atmosphere, affecting the chemical composition of the air and oceans. As these eruptions became less frequent, the Earth had the opportunity to replenish its oxygen reserves and initiate long-term changes in atmospheric equilibrium. Active eruptions occur much less frequently now, and far less mercury and sulfur dioxide are emitted. Mercury, now less common, is fixed in stable compounds, settling in sediments or being absorbed by organisms. Sulfur dioxide becomes less noticeable and no longer poses a threat to the ozone layer. This chemical respite contributes to the ozone layer's restoration, which is necessary for filtering ultraviolet rays from the sun. It takes several thousand years for the ozone layer to recover, and its recovery is associated with a reduction in A. I've often wondered about the moment our planet started to breathe again. After so much destruction, the gradual restoration of the atmosphere really an incredible thought. It provides a shield, you see, against the harmful effects of ultraviolet radiation, those rays that, paradoxically, play such a vital role in the development of life itself. On the continents, I imagine plants slowly colonizing new spaces, while in the seas, photosynthetic organisms finally receive the light they need. Chemically, the restoration of the ozone layer contributes to a stable balance of redox cycles. It's a delicate equilibrium, really. The planet begins to find its balance between the oxygen produced by living beings and its consumption through respiration or the oxidation of minerals. This regulation, this natural fine-tuning, ends a more stable environment, and it's in that stability that organisms can truly thrive. Organisms that depend on a constant supply of oxygen and reliable protections from the sun's radiation. Although volcanoes remained active, their eruptions became less frequent. The gas emissions dwindled, became so insignificant that they could no longer cause major changes. In this less saturated atmosphere, oxygen circulated more freely between the oceans, the soil, and the various ecosystems. Marine life flourished thanks to the greater saturation of water with oxygen, and forests thrived in the cleaner air. Then, around 240 million years ago, atmospheric oxygen levels stabilized at around 15 to 18%. While slightly lower than what we have today, that concentration was sufficient to restore biodiversity. On land and in the oceans, the soils teemed with crabs, diligently decomposing organic matter and releasing vital nutrients. On the continents, well-rooted forests absorbed carbon dioxide, those silent giants constantly working to maintain the balance of nature. And so, gradually, a new environment formed on Earth, a more favorable environment for life to flourish once more.